Let me just X out the thing I opened. And actually, before we get started, a little bit of review. We talked a little bit about what, or here's a little bit about what pitch is, musical pitch, right here. So all sounds are caused by vibrations when we're talking. Another way you can know this is like, if you put your hand on your throat, you feel it vibrating. These vibrations are the things that are causing waves and for sound to travel. And that's why we have these like peaks and lows when you actually graph sound. But when these vibrations occur at fairly consistent frequencies, kind of like it's periodic, we perceive them as musical tones. It's kind of like music. And a little reminder that we've been studying like sine and cosine waves. They look very smooth, they have particular properties about them that you can see right here. So let's go ahead and go back to this summative, and let's test out this live sound analyzer. You want to make sure that it is just a few seconds that you're recording your sound, which should be musical, and I'll give some examples. Now, for this summative, I'm only going to be concerned about the audio version of this. I want you to also notice that the time is in milliseconds, so it's very quick. That's why it's kind of like I'm going to record very quickly what sound you're making, and here it has the amplitude. So milliseconds, and we have the amplitude of our waves. Okay, I'm going to go ahead and just start talking right now. So hello, how is everyone? I pause it, and you see kind of like different kind of waves happening. As I was talking, it doesn't really look much like a sine or cosine wave. It has a lot of like bumps to it. I'm good. How are you? Take a look there. That's even less sine wavy. I mean, there's some portions of it that looks sine wavy, but then there's parts that don't. Now, a constant pitch is going to give us something that's more periodic, has repetitions in its y values over some domain. So let's try to see how we can get some sound that will be musical. Now, there are two different ways you could do this. If you actually have an instrument like a piano and you push a key, you'd create that noise, a constant pitch, that music. Guitar, same thing. There is like a constant note. Different ways you could do it with an instrument. But let's say you're like me, you don't even own an instrument. So here's some tips. Unless you find some other thing you can do that will create a periodic type of function. You could also sing a vowel like A, E, I, O, U. So singing a vowel. So let me show you. Let me try to sing the vowel E. And again, this has to be quick, and you probably have to test this out a few times. So E. That was me trying to sing E. This kind of looks periodic, but I mean, I could do better. So I think I'd record again. So like, for example, periodic means the graph, its shape is repeating over time. Our formal definition, of course, is over some fixed domain, our output values are repeating. So these look similar, but then it kind of gets smaller. Probably I dropped my E sound or something as I was kind of recording this. I got more shy and it dropped down. So let me try something else. I also am thinking, woo, this is going to be a little bit tricky to model, right? Because in the end, we're going to try to model our sound. It's going to be a little bit tricky because this looks, it does look similar to what we've been learning, right? Sine and cosine waves, but it does look a little bit different. So I'm going to go ahead and clear my screen. Let's try something else. So that was E. Let me try O. O. So there's my O sound. Again, it does have a periodic nature to it. We do see repetitions happening. I see this thing is getting repeated over a fixed domain length. That is what makes this periodic. But let's say I want to test something else. And again, you all are free to choose whatever it is that creates a periodic function. Again, if you want to tackle on how to model this, right? Because later you're going to be making your equation and modeling this. You could check that out or try it out. Let's try some other vowels. Let's see what's one I haven't tried. So I already did E, I did O. Let me try I. I. So again, that was me trying to sing pretty horrible. I don't really see much of a constant pitch happening there. So let's try another one. I'm gonna try O again. Let me try to actually sing it. Oh, ooh, was almost there. Oh, ooh, that's looking better. So you see how this is kind of taking a little bit more time and and especially if you can't sing like me. I am so sorry you have to listen to this so I could do this example, but this is us trying to get something that looks like a wave like nature that we've been studying, and we're gonna try to model it. I like this one. I'm gonna stick with this. So I'm gonna choose this O that I tried to sing. I need some vocal lessons, as you can see. But anyways, so that is how we are using this tool. Again, as a reminder, this is measuring in milliseconds, so it's very quickly. Here's our amplitude. Take a look at how small the scaling is on the amplitude. In addition, when you need to measure, for example, your periods, we talked a bit about how to measure period is you measure from peak to peak of a function or a sine wave or cosine wave, right? What that means is we're basically measuring the length of this. What's cool about this tool though, y'all, is it has a measure button. Let me just click on it and you can actually move this to measure. So for example, my period of the O sound that I just tried to sing is going to be time. So my input is time for this example. It's about 3.65 milliseconds.